Hello, everyone. My name is Caden Cronenberg, and today I'm going to talk to you about our capstone project, which is the Camera Directed Driving Endeavor, or CADD-E for short. So CADD-E is a self-driving golf cart system that we're designing to be capable of autonomous transportation for the first 9 holes at Lawrence Country Club. So this is our team here.
Hey everyone, I'm Song Wood.
I'm Justin Caesar.
Hi, I'm Alex.
Hi, my name is Joe Nordlane.
My name is Caden Cronenberg.
So this diagram shows CADD-E's different subsystems that work together to achieve autonomy. So there are 2 broad categories of subsystems. So in blue is the perception systems, and in orange are the decision-making systems. So the perception systems receive information from the cart's sensors and map in order to estimate the car's state and to build a representation of its surroundings. And then the decision-making systems plan and carry out actions through the car's actuators. So the throttle, the brakes, and the steering. And that's all done in order to navigate from wherever the cart is currently to a fixed destination, while also satisfying some constraints like avoiding obstacles and staying on the cart path. So I'll describe what I've been working on in the perception systems. So starting with the offline map, which is basically a graph data structure that represents the area that we're going to be navigating. So to do this, I took data from OpenStreetMap and I constructed a directed weighted graph where all of the vertices are waypoints from OpenStreetMap, like these yellow dots here, that outline the cart path. And this diagram here kind of shows the map representation a little bit better. So all of these red dots are vertices in the graph, and you can see that they outline the cart paths for holes 1 through 9 at Lawrence Country Club here. So now that we have the map, we can start to kind of figure out where we are within that map or graph. So we do this in the localization module. So here we take sensor data and we will determine where we are relative to the map. And for this process, we're going to primarily rely on GPS data to know where we are on a global scale. And then we'll find a vertex on the map that's closest to this position. So GPS will give you accurate coordinates down to about a meter, but we want some better precision than that. So we're going to use real-time kinematics or RTK corrections, as well as a Kalman filter to refine the GPS signal. And between those 2 techniques, we should be able to get our precision down to about less than 5 centimeters. So now that we have a map and we know where we are on that map, we could start to plan out a route to a destination that's specified in the UI. So because our map is implemented as a graph, we can just use Dijkstra's algorithm to find the optimal route from where we are to where we want to go. And then we deliver this route as a list of waypoints to the next module in the system, which is the path planner.
I'll now talk about the user interface portion of our project. So ultimately, we're going to have an 8-inch touchscreen that is going to be mounted onto the dashboard of the golf cart. We just created an initial prototype in Sprint 3 consisting of a React front end, and we are planning on utilizing Node.js on the back end for the live mapping and to allow the serial communication between the touchscreen and the embedded systems to ultimately allow for the user to interact with the cart, starting and stopping and planning routes. I'll now proceed to a demo of our initial UI prototype. Here's the initial prototype for the UI that we developed during Sprint 3. As you can see, this is just a very basic layout of what we want the UI to consist of. We have some of the basic functionality with the states, such as when you press the go button. As you can see right now, the speed just jumps from 0 to 17 miles per hour. We're going to work on dynamically changing that and having animations so it looks a lot better. You can increment the counter for the tee box with this next tee box button. And moving on to the map side of things, right now this is just an embedded HTML iframe from OpenStreetMaps of the Lawrence Country Club, which is the course that we'll be navigating. And we just have a static marker beginning at the first tee. Ultimately, like I said, we'll be using Node to have the live GPS location and implement the route planning, such as when the user presses either the next key box or the next screen buttons.
Another important aspect of a self-driving golf cart is the collision space identifier. This module consists of 3 different attributes: the lane identification, obstacle detection, and obstacle path prediction. Lane detection, as seen in the bottom right, is detecting where the path we are trying to drive on is within the video frame itself. And so originally we were just using some edge detection to kind of find the edges of the path and then figure out where the vehicle is relative to each edge. And we can see an example right outside of engineering of this model happening. Next is object detection, which can be seen in that photo in the bottom, which is detecting where people are, mainly people, but in addition also golf carts, where they are in the image relative to the golf cart itself. So if someone's, in the very edge of a frame, they're not going to be as noticeable as obviously in the middle of the frame, which is where we need to detect whether or not, if the golf cart is driving at them, whether we are going to hit them or potentially drive right past them. And that leads into object path prediction. So once we know where the path is and where we know where all the objects are within the image, we can then predict what the object is going to do within the next couple of seconds. And so this is important because if someone is walking towards the path, we want to slow down before we get right up close to them and then slam on the brakes. So we can have kind of a more gradual slowdown instead of that instantaneous stop. And so this is mainly done by detecting which direction the objects are facing, the golf carts and the people, and then making a prediction on if they're moving towards the path or away from the path and adjusting the speed of the cart from there.
Next, we'll discuss the motion planner module, which is the driving force behind the decision-making aspect of the architecture. What the motion planner does is you take a reference trajectory, a representation of the collision space, and the actual information from the IMU, the car's state, in order to plan a trajectory which minimizes a cost function. And what that cost function represents is things that we want to avoid in our trajectory, like changes to the car's acceleration, which we want to minimize because they can cause passenger discomfort, and the amount of energy the car uses. The way we do that is by using a model predictive control approach, which is essentially an approach that uses a mathematical model of the car to predict what impact certain inputs would have on the cost function. And so you can search basically over the space of possible inputs in order to find the one that minimizes the cost function using this model. What do we do with those trajectories? Ultimately, they're fed into the controller, which takes those high-level commands like turn the steering wheel left 15 degrees and turns them into electrical inputs that we can actually send to the motors, which control the steering, throttle, and brake. So how we represent this and how we test this motion planner is by using a MATLAB Simulink model. And you can see there's basically 2 modules in this. There's a motion planner, which feeds commands into a vehicle environment module, which simulates the car and the car detecting features in the environment. So for example, one scenario we might load into this is this lane keeping curved road situation where the car has to continuously adjust the angle of the steering wheel in order to stay on the road. You can see the car is the blue box. There are 2 sensors on the car. The blue field is the camera and the red field is an ultrasonic sensor. This situation will only use the blue field of the camera, since all we need to do is detect the boundaries of the lane, which is, you can see that being done in those red lines. Those red lines represent what the camera is detecting as the lanes. So it uses those, it combines those into a previewed curvature, and using that previewed curvature, the controller can basically stay on this curved road, which you would see if we had a video.
A very important part about making a self-driving golf cart is being able to control all of the systems digitally in order to make them autonomous. And I'm going to speak a little bit how we plan on doing this on the 3 main systems: the braking system, the throttle, and the steering system. So for the throttle, we plan on using a digital potentiometer and Arduino implementation to control it digitally. The reason why this works is because a golf cart already uses a potentiometer, a physical one, whenever the gas is pressed to increase the speeds. So simply converting this into a digital implementation and controlling it with our code using Arduino should suffice. For the steering system and the braking system, we plan on using linear actuators. And for those of you that don't know what a linear actuator is, here's it right here. So we plan on, for the steering specifically, we plan on pushing and pulling the wheels using the linear actuator, heavy duty one, and having a microcontroller, which then interfaces with the linear actuator and allows us to control the actuator using a Arduino. For the brake-by-wire, the system is going to be very, very similar, which allows us to reuse all of our code. The only difference is that the linear actuator will be pulling the brake to make the cart slow down and releasing it to release the resistance.
So that's our project so far. Through the remainder of this semester and next semester, we're going to continue developing all of these subsystems, with the end goal being one unified system that can complete the task of autonomously driving the first 9 holes at Lawrence Country Club. Thank you for your time.